Hello, welcome to the first lecture of ECE 141 on digital communications. And basically, I will introduce to you digital communication systems, or actually just a review for those who have taken EEE 107. I expect that you have already learned some basics about digital communication systems, and we'll review them. So you'll see the outline of this lecture from the subtitle right here. Okay. So we're going to discuss the digital communication systems, how we transform your analog communication system into a digital one, and some preliminaries of digital communication systems, or the first quote-unquote digital communications from before. Okay? So just to review, communication, according to Hykin, from the book, okay, or from our reference, communication involves transfer of information from one point to another. Okay? So I've highlighted the important points. We're already doing it as humans. We're using our voices to create sound waves, okay, and communicate with each other. So we're actually one communication system. So some information is sent from the mouth, from the brain to the mouth. So the brain generates information, the mouth shapes that information to a suitable form, and then it's going to be transmitted over the air, and the ear will transform that information, that physical manifestation of information, and send it to the brain of the receiver. Okay? So this is actually a communication system. So it facilitates the transfer of information from one point to another. Right. So the basic elements of a communication system is there is a source, the information source will be the input to an encoder, but you actually know this as a modulator. For a digital communication system, we call it an encoder. Right? And the encoder transmits the information to a channel where it will be distorted by external factors. So we can't do anything about that. It's inherent in all channels. And it will be received by a decoder, or what you know as a demodulator. And after that, it will be sent to the destination. Okay? So the source, again, generates information. So the information represented as signal. Right? If we go back, the source is generated from the brain, and it is shaped by the mouth as a physical signal. The channel is the abstraction of a physical medium. So the channel will distort any information or any signal that you send through it, and we can't do anything about that. So some of the impairments would be your signal attenuation. Your strong signal from the transmitter will be weak on the receiver. Some noise, distortion due to other factors, like if you're in a wireless channel, the waves will bounce off from your environment and will be received by the receiver multiple times, etc., etc., and some interference. Maybe some other user is transmitting. You can actually think of it in terms of human communication system. Distortion arises when there is an echo. So if, example, you're in a church. So you're in a church and you try to listen to the priest, and the church normally is very big. When the priest tries to speak through the sound system, the sound will echo everywhere, and sometimes the homily, or what the priest is saying, is actually indiscernible. So that's an example of your distortion. Hi. So the encoder converts information to a suitable form for the channel. Normally, you know this as the modulator. And the decoder just reverses that operation. So let's look at it deeper in a finer view. So this is now your digital communication system. We have digital sequences or bits as the interface between your source coding and channel coding. Okay, so we have what we call a source encoder and a channel encoder. The source encoder would represent your message into bits, and the channel encoder will actually process the bits to a suitable form to go through the channel. Okay, so the reason why we separate these two encoders is because it's cheap and reliable and scalable. If you do it using one block, it becomes complicated. Okay? So if we separate them, it becomes easier to debug the system, becomes cheaper, becomes scalable. Okay? Source coding is, if we look at it deeper, is basically your signal, physical signal, will be your physical signal, sorry, will be digitized. Right? So this arrow should be facing to the other side. Apologize for that. Okay. So if you have an input waveform, it will be digitized. So what does digitizing mean? It will be sampled in time, it will be discretized in amplitude levels, and it will be encoded into bits. Right? That's one way we can represent a physical information in the digital world. Alright? So the receiver just reverses that process. You have a binary sequence, it will be decoded, and from a lookup table, it will manifest as a physical signal, and a filter will be used to remove the high frequency components, and you have your output waveform. So the channel coding part is not much, but it's more complicated. So I have a sequence of bits from our source coding block. The channel coding will have an error correction block here, something that you won't see in an analog communication system. So after error correction, it will be fed to a symbol mapper, and the symbol mapper will be shaped into pulses. So you have a manifestation of a physical signal. Right? So just some note, digital signals cannot exist in the real world because the real world is analog. That's why you have a digital symbol right here. It will be fed to a pulse shaper. This pulse shaper will be the physical manifestation of your signal through the channel. The receiver part just reverses everything, as usual. Alright. So how do we convert your message sequence into an analog sequence? So the easiest way is to sample it. How do we sample them? So we sample them by taking the values at different points in time of your analog signal. And the different points in time would be equally spaced by t sub s, or the sampling period. And how to do that? Basically, you just multiply your message waveform with your what we call impulse train right here. So we multiplied the message with the impulse train, you get your sampled signal right here. Okay? So note first that this S of t is band limited, and it is sampled as I said earlier, sampled at a uniform rate of 1 over ts. This is the sampling frequency. And the analog representation, the mathematical representation of your sampled signal is basically just a sum of your your original signal and multiplied by an impulse that is time shifted, and you sum all that and you get your message signal right here. Right? The sequence S of m is the sampled signal. This is what you can use to represent it in the digital domain. Okay? So to solve for the Fourier series of the impulse train, well, since it's an impulse train, basically it's a periodic signal. So we expect the we expect the Fourier transform of your impulse train to be also a discrete signal, or a discrete Fourier transform also. Okay? Turns out actually that our Fourier transform, the Fourier transform of your delta train or impulse train is also a delta train with amplitude 1 over Ts. So if the synthesis equation becomes this. So basically, it's still an impulse train in the frequency domain, but with a scaling of your sampling frequency. Okay? So recall that a pointwise multiplication in the time domain is a convolution in the frequency domain. So the signal, when multiplied by the impulse train, when we look at it in the frequency domain, this impulse train is still an impulse train. This signal is band limited. That band limited signal will be convolved by this impulse train. Okay, so it results into this frequency domain of the sampled signal. Basically, right, let me highlight that. Okay. So this part of your sampled signal is called an alias. Right? And this part is also an alias, and this is your original signal. Right. To recover the information, we just need to get the original signal and filter out all the aliases. So the ideal filter for that would be your rectangular pulse filter, right here, or the ideal low-pass filter. And from the sampled signal, you get your message waveform. Okay? So if the original signal is band limited, it can be recovered using a low-pass filter, ideal low-pass filter. Okay. So information from a sampled signal can be recovered if the sampling frequency is twice the maximum frequency of your signal. If we don't do that, then we have an overlap between your aliases. So these aliases overlap with the original signal, and their frequency domain equivalent will look like this. Okay? We call this a spectral folding. And when you try to reconstruct the signal, so if we try to reconstruct the signal, then we're getting the signal right here. And as you can see, instead of a triangle signal, then we have some distorted form of your original signal. So this distortion cannot be reversed. You always need to sample more than twice the maximum frequency of your original signal. Okay? So as you know, this is what we call aliasing. So in practice, we cannot really produce a delta train or an impulse train. In reality, we can actually produce a rectangular pulse train. We can still sample with that, no problem there. Okay. But the frequency domain equivalent of the signal will be different. Right. So you have we can still multiply this rectangular pulse train with the message waveform. We call this natural sampling. And then what that means is that your sampled signal is just the same. You multiply your original signal with the pulse train. Okay? The pulse here, P of t, is the rectangular pulse. So what happens to its frequency domain equivalent? Well, it will be scaled. Right? So recall that when you multiply in the time domain, you get convolution in the frequency domain, and the frequency domain equivalent of a pulse train is the sinc function. Sorry, right here. There you go. And what happens is that your frequency spectrum would be scaled at different parts of your will be scaled at different frequency shifts of your signal. Okay? So it will be scaled. There you go. So just some remark. Your sampled signal occupies a large bandwidth. And the main purpose of pulse shaping is to limit the bandwidth of your digital transmission. So we can actually transmit the signal using this bandwidth. It's already effectively a sampled signal. Okay? As compared to your bandwidth from using an impulse train, you're gonna actually use the whole frequency band just to produce your impulse train. And that's one advantage of your using a band-limited signal or a rectangular pulse train as compared to your delta train. Aside from the delta train being not realizable in the real world. Right? So this is your sampling. So this is the first step of converting your analog waveform to a digital waveform. So after sampling, you're discretizing the sampled signal. So basically, you make the signal, how do you call this? You basically assign a value to the sampled signal such that it can be supported by a computer. So recall that a computer can only have discrete values or can only be represented by discrete values. Right? So for example here, as you can see in the graph, this is your original waveform, the one with the smooth curves. Alright? And the sampled signal would be from here to here, here going here, here going here, and so on and so forth. However, the computer cannot represent that much continuity. Therefore, we round up the signal to its nearest level. Okay? So these blue lines represent the amplitude levels of your quantizer. Okay? And this process of rounding up. So rounding up the sampled signal, we call it quantization. Okay? So if you are, for example, if you sample from here to here, the signal is right here, right? It will be rounded to the nearest level, either here or here, depending on how far it is from that level. So this process is called quantization. Okay? And because of this, we have some form of error. That error is called quantization error, and it's computed as your discretized signal, D sub m, which is the red ones, minus the value of that signal at that time. Right? From the figure, the quantization error falls between delta V, negative delta V over 2, and delta V over 2. Right? And this delta V is basically the difference between two levels. Okay? So difference between two levels, that's delta V. Right? Can also be thought of as the difference, if you get the total difference from here to here, from A max to negative A max, and you divide it by L levels. Okay? So assuming the error is equally likely, since this is a random variable, right? The mean square quantization error can also be thought of as the quantization noise, all right, is equal to this value right here. Right? So this is the value of your quantization noise, and it's actually dependent only on the quantization step. So this is actually amazing if you think about it. It's a random variable, but we can think of it as an added noise because of discretizing the sampled signal. So this is what you won't see from an analog communication system. If we convert the analog signal to a digital signal, we already have noise, whose value is delta V quantity squared over 12. So as you know, if you increase the number of levels, So you increase the number of levels. So if you increase this, delta V goes down. And if delta V is down, then the quantization noise also goes down. So what's the downside to that? You need more levels. And more levels correspond to more bits. But I'm getting ahead of myself. Alright? So just to summarize, alright, so this quantization error is noise, basically. And we define a signal to quantization noise ratio. Basically, it's just the signal power divided by the quantization noise power. Right? And it turns out it's just this, as we saw earlier. It's just the power of your signal divided by the quantization error. Right? So, as you can see here, the levels are of uniform differences. So the difference from here to here is the same as from here to here and from here to here. Right? There's actually a problem with that. So the problem is, what if the signal fluctuates from a very small fluctuation to a very large fluctuation? An example of that is our voice. This is an example of a voice signal. And as you can see, there are parts of on the voice at which the fluctuation is small and then it becomes large. It could peak at a very large point. Right? So this is an example of a signal that has a large crest factor. So the crest factor is basically the maximum value of the signal divided by the average. Right? So the maximum peak power divided by the average power. If we're gonna quantize this signal uniformly, so a problem with that is if we try to quantize it to accommodate the little fluctuations right here, we need to have a larger or more levels just to be able to recover the small fluctuations. But that means we need more bits to represent the signal, and more bits means more complexity, more processing power, more expensive devices. The solution to that is actually using non-uniform quantization. Instead of having uniform differences between your discrete levels, differences between them would be non-uniform. And this is actually what is used on our phones. However, non-uniform quantizers are also expensive. So how do we solve that? You're actually already familiar with this, I hope. We use companding. So companding is basically a word that is, how do you call this? A word that is companded, or a word that is combined, meaning compressor, or compressing, expanding. Okay? So you compress the signal at the transmitter side, and then you expand it once it is received. Doing that, we effectively have, we effectively amplify the small signals and attenuate the large signals. Right? So we amplify the smaller signals and attenuate the large signals, so we can limit the amplitude levels from a signal. Right? And that will be fed to a uniform quantizer. After which it will be expanded, okay? And then it will be reconstructed and you get your original signal. And there are two techniques to do that. So what is actually normally used is the logarithm function. So we have the mu law and the A law. Mu law is, I believe, is a European standard. A law is an American standard. Right? And depending on different levels of parameters, well, you get some form of logarithmic function. Okay? So as you can see here, the smaller levels are actually amplified. So it has a large slope on this point. At the higher levels, the slope becomes less. So any fluctuation at this level will actually be confined from here to here. Right? So if we have a small fluctuation, right, small fluctuation from here to here, so let's say the signal fluctuation is from here to here, okay, oops, there you go. Then the output signal will fluctuate from here to here, therefore expanding or amplifying the low-level signals and effectively attenuating the high-level signals. Right? Right. Finally, we encode our waveform into bits. After quantizing, we now encode this waveform to bits. So remember that we have discrete number of levels, and depending on the number of levels is how many bits we use to represent them. So if we have three bits, that means we have 2 to the 3 possible combinations of bits, and that is equal to 8 levels. All right. So we use 3 bits to represent 8 levels. If you want more levels, you need more bits. 2 to the 4 means, I don't know what is happening. 2 to the 4, okay, there you go. 2 to the 4 means 16 levels, right? And this coding technique is what we call pulse code modulation. Okay, so this is your pulse code modulation, and we will actually talk about this more in the next meeting. Okay, so that ends this part of your course. So this is the end of lecture 1. I hope you learned a lot. If you have any questions or comments or clarifications, just leave a comment below. Okay? I'll try to answer it as soon as I can, as soon as possible. I'm always online, as you know, as a millennial. No, I'm kidding. I'm always online, and I will try to answer your questions as concise and as understandable as possible. See you next meeting.